Okay, so we left off with testing this model of the bunny population that involved what is hopefully a more realistic assumption about how bunnies actually behave, which includes this 1 month delay to maturity. Alright, so I'm not going to list all the assumptions that led to this model again. It involved the bunnies not dying, having an ideal environment, plenty of food and water. We start off the experiment by buying a male-female pair of immature bunnies from the pet store. It takes them a month to mature so that they can reproduce. And once they are mature, every mature male-female pair will reproduce once a month, creating one new male-female pair of bunnies, which begins as immature. Okay, so I'm not going to write out all those again. You should have them in your notes. They're in another lecture, in the previous lecture. So you have them somewhere. Now, we left off with an assignment, which was to fill in the rest of this chart, describing the growth of the bunnies. So I'm just going to run through it again. My charts in the last video were kind of a mess, so I switched to having these lined paper kind of background here. Hopefully that makes it a little better. So we start off with one immature pair and no mature, giving us one total pair of bunnies to start. Now this immature pair matures by the next month, and we haven't had any mature bunnies yet, so there haven't been any ones to reproduce and produce any new immature pairs for us. Alright, so our lack of mature pairs at the beginning gives us a lack of new immature pairs now, right, in the next month. Okay, so all told, we still have just one total pair of bunnies. Okay, so now our mature pair, right, what color am I using here? Orange, right, our mature pair now has offspring, right? They're finally mature, so now they can actually reproduce. So they have one pair of offspring in the next month. That's why I'm going down a line every time I do this. I'm going to the next month. And we didn't have any immature pairs in right here. We didn't have any immature pairs. So there are none to grow up and become mature along with this one pair we already had. Alright? So we still just have the one mature pair from before. And now we have one new immature pair because they were able to reproduce this month. So in total, that gives us two pairs. Okay. Now this is where things start to get interesting, start to get a little more complicated. So our mature pair this month reproduces, and they make one new immature pair. Our immature pair from last month has now matured, and they combine with our other mature pair. So now we have two mature pairs and only one immature. Alright, so in total, this gives us 2 plus 1, which is 3 pairs of bunnies. Okay, now, let's see what's going to happen here. Our immature bunnies will again mature, right, because it takes them 1 month, so they're maturing again. This new pair of bunnies is maturing. And we had 2 mature pairs before. We add 1 more to that. That gives us 3 total. And now these 2 bunnies, right, these 2 pairs up here, they are reproducing, and each one of them is making a new immature pair. So now we have 2 immature pairs here. Alright, so our new line for month 4 is 2 immature, 3 mature, 5 total. Alright, just keep on doing this. This 2 pairs of immatures will mature and combine with these 3 matures here to give us 5 total. And our 3 mature pairs are going to create 3 new pairs of offspring, 1 pair each, for 3 total new ones. Alright, so that adds up to 8 total pairs. All right, again, these 3 immature pairs are going to mature, combine with the 5 mature to become 8 total. These 5 mature pairs each produce 1 new pair of offspring each, so that's 5 new immature pairs. So the new line total is 5 plus 8, which is 13. I'm not going to keep drawing the arrows because I think that might just make this a little more muddled than it needs to be. The next line is going to be 8 immature from our 8 mature last month, and our 5 immature grow up and combine with the 8 that are already there to give us 13. Adding those together, you get 21. And the next month, we're going to have 13 new immatures, 8 plus 13 new mature, that's 21 new mature, 13 plus 21 is 34. All right, the next month, we're going to have 21 new immatures, 13 plus 21, which is 34 new matures. That's going to give us 21 plus 34 is 55 new pairs, or total pairs, sorry. At the next month, we're going to have 34 immatures, 21 plus 34 matures, so that's 55 matures. All told, that is going to be 89, 34 plus 55. All right, now we have 55 mature pairs, and we have 34 plus 55, we have 89 mature. Adding those together, we're going to have 130 plus 14, 144 total pairs. And our last line here, whoops, wrong color. We're going to have 89 immatures, and we're going to have 55 plus 89, which I just figured out is 144. Total mature pairs. Adding these together, let's see here, you're going to have 144 plus 90 would be 234, so take 1 off of that is 233. All right, so 233 pairs at the end of our 12th month. All right, so I shouldn't say we have. Our model predicts. $233 pairs. When the time is equal to 12 months. All right, when t, the time that we've run the experiment, is equal to 12 months. Okay, so let's compare this to our old model. Right, this was the model that lacked a delay. All right, so newborn bunnies were already reproducing in our old model. So compared to our old model predicted, oh, it was something crazy. Was it 2,000 or was it 4,000? I think it was 4,000, right? On the order of 4,000 pairs at t equals 12 months. You know, I'm not a bunny scientist by any stretch of the imagination, but it seems like one pair of bunnies turning into 233 pairs of bunnies after 1 year versus turning into over 4,000 pairs. I think the 233 seems much, much, much more realistic. It may not be perfect, but this seems way better. And by better, I mean more realistic. All right, it just seems like a gut feeling kind of thing. It seems like it's way better than our previous model. Okay, so that's very good. A downfall of this is that 233 still seems kind of high. This could be addressed in a variety of ways, right? Because always the goal with modeling is to create a model based on what you think are reasonable, but tangible, like easy to work with, very manipulatable assumptions, right? Very workable assumptions. And usually there's a trade-off, right? There's always a trade-off in math and in life. In math modeling anyway, there's a big trade-off that happens where the more realistic you make your model, the more mathematically intense it gets. All right, to the point that having a truly realistic, I'm doing air quotes, but of course you can't see that, but to have a quote-unquote realistic model of something that is extremely close to true to life, the math can sometimes be pretty close to impossible. So, there's a trade-off that has to happen here. In order to make the math workable, to actually be able to get pen and paper predictions from a model, that means that you have to make some concessions in your assumptions, okay? So 233 seems like it's probably still a little high, right? That seems like just gut feeling that might be too many bunnies at the end of 1 year. I don't know that for a fact, so more research would be necessary here, but it just seems like it might be a little high. So there are many, many, many ways that you could improve this model. So for instance, one thing that you could do would be to look into what the actual delay to maturity for your standard, and again, it's going to be dependent on species, but whatever the most common species of bunny is in North America, for instance, or in the Mid-Atlantic, right, in New Jersey. Just be as specific as you want to be. What is the normal delay to maturity? Maybe it's not 1 month, maybe it's 3 months, maybe it's 6 months, right? And then you could tweak this, this model gives you like a prototype for how to actually approach a problem like this, because then you could take this idea and you've already done like the vast majority of the hard part, right? You've done the vast majority of the hard parts of this modeling problem. And again, this is why getting your foot in the door is so important, okay? So you've gotten your foot in the door, and now you just need to push that door open a little farther. And the way that you could do that would be by figuring out what the actual delay to maturity is, and then creating a new table of values that addresses that new, better, more realistic information. All right, another thing you could do would be to figure out the average litter size. Right, we're assuming every month that there's a litter of 2 bunnies. Well, maybe on average it's actually like 14 or something. Now that would be an issue because that would make our numbers at the end of 1 year actually way higher than what we got here. But this is another thing that you could do. The other, I would say, reasonably easy is not the right word, reasonably straightforward. And remember, I said in a previous video, straightforward does not mean easy. Another reasonably straightforward thing you could do would be to figure out what the actual gestational period is for New Jersey bunnies or Mid-Atlantic bunnies or whatever bunnies you care about. All right, how long from conception to birth of a litter, right? Maybe it's not 1 month like we're assuming here. Maybe it's less. Maybe it's 6 weeks, a month and a half. Maybe it's 2 months. I have no idea. But this is another thing that you could do. And again, you've already done the hard work of creating the model in the first place, tweaking it a little bit to change the gestational period, change the litter size, change the delay to maturity. These are all things that now that you've got the template in front of you, you could reasonably do these things. Okay, so there are ways to make this much, much, much more realistic. Simple ways, straightforward ways to make it more realistic. All right, but I think regardless of how realistic it actually is to like the numbers of bunnies, I hope that you all agree with me that compared to the 4,000 prediction, this is just hands down seems much, much better. Okay, so that's really the most important thing that I want you to take away from this. Now, in terms of this operative word here, predictions, right? This is really the critical thing that a model has to be able to do. It has to be able to make predictions. So, if you look at how we went about the actual mechanics of making a prediction for this set of bunnies, it was fairly brutal, all right? Extremely brute force. We had to go line by line, column by column, and figure out one at a time what every single one of these new values is going to be. And this is just a rough way to do it, all right? It uses a lot of lead or ink. It uses a lot of paper. It uses a lot of brain power. And most importantly, it uses a lot of time. And time is the most precious resource of all. So we don't want to use time any more than we have to. So here is what I propose we do. I think we should actually come up with a formula, if possible, that this model actually predicts the bunnies will adhere to. All right, so predictions here. I say, for saving ourselves time, we want a formula that predicts the bunny population. Oh, misspelled my own abbreviation. All right, that predicts the bunny population at any given month. So to do this, I want to introduce a little bit of notation. All right, so these bunny populations, all right, I'm going to sort of underline or put in boxes the operative things I want here. So, for instance, at month 0, our total population was 1. All right, so this indicates the time, and this 1 indicates the total population. So I'm going to give this a name. Just for simplicity, so when I write it down, we'll all know exactly what I'm saying. All right, I won't have to write out a giant English sentence every time I want to refer to something. So I'm going to refer to this population at month 0. I'm going to refer to this by the name R with a subscript of 0. All right, so R for rabbits, right? That's all that means. It's just the rabbit population. I'm calling it R for rabbits. And the subscript tells me what time it is. All right, so my time is in months here. So I'm going to say, what month do I care about? All right, that's what that 0 tells me. All right, so for instance, R sub 0, let me write these off to the side here, is 1. This tells me that the rabbit population in month 0 is 1. That's what that notation means. Rabbit population in month 0 is 1. All right, let me grab another one here. I'll use a different color. Month 1. All right, that's my time, month 1. My population is 1 again. Using the same notation, I'm now at month 1, so my subscript is going to be 1. Is equal to 1 again. All right, I still just have 1 pair at the end of month 1. All right, let me grab a random one here. Let's do it in purple. Let's grab maybe time 5, month 5. And if I walk over here, I see the population's 8. All right, so R, and now I need to say what time I'm looking at. The time is 5, month 5. The population in month 5 is 8. All right, so this is the notation that I'm proposing we use to describe this bunny population. And in particular, let me jump down here to the very end. Month 12, my population is 233. So we would write that as R sub 12 equals 233. All right, so this is the notation that we're going to use to describe our bunny populations. All right, so I can rephrase this, our model predicts stuff. I can rephrase this in a very, very succinct way now. Right, so let me just show you how that would look. So here, our with a delay, right? Our model with a delay, R sub 12 is 233, and without a delay, R sub 12 was something like 4,000. I'm using the squiggly equal sign to say, I don't exactly remember what it was. 4096 maybe? 4050, 4096, it might have been 96. Anyway, it was around 4,000, all right? So this is a very quick way of just saying exactly those paragraphs or those sentences that I wrote before, just in one simple line, all right? Before R sub 12 was around 4,000. And now when we introduce a delay, R sub 12 is around 233. Okay, so this just gives you a very fast way of comparing these things. And, you know, you always want to indicate your units when applicable, just so we are sure that we're talking about the same thing, right? You always want to compare apples to apples. So 233 pairs versus 4,000-ish pairs. Okay, so here's what I really want. Right down here, when I said that I want a formula that predicts the bunny population, now we can say what we really want. We want a formula for R sub n. And here, n is absolutely any month number that you could ever want to know about. All right, so you made a table that goes to month 12. Well, what happens if you want to know what happens in month 15, or month 18, or month 36? Right? You don't want to make a table that has all those months built into it, especially if you don't already have the first 12 months in front of you. Right? If you don't have a ready-made table sitting on the desk in front of you, and you're asked to figure out what the population is in month 36, you're going to start from scratch, right? You're going to start at month 0, and you're going to go all the way up to month 36, and it is going to be awful, right? It's not going to be fun for anyone. So this is what I really want. I want a formula that's going to predict what Rn is for any month number that you want. That's what n represents here. It's whatever month number that you're talking about, be it 1 or 12 or 16 or 36 or 110 million, right? Whatever the number is, I want to be able to figure out a formula for the population in that month that you are asking me about, no matter what that month is. All right, so before we try to do it for our fancy model that has a delay built into it, let's just try to take a step back. Can we do this for our old model, meaning the one that has no delay in it? All right, I rewrote just the first few months of the table down here for simplicity, just so we all have it in front of us. Now, what we're doing here, right, we've got, right, this is R0, this is R1, R2, R3, and so on. Oops. And R sub 6 is the last one I wrote a value for. All right, so here's what we want to do. We want to look at these totals and see if we can figure out a formula for them based on the time that they correspond to. All right, so we want to find some kind of pattern that links the time that you're looking at with the population that you're looking at. All right, so one way to do this is actually to look straight down the population column, the total population column. What happens to the population every month? All right, this is one way, again, to get your foot in the door and get started with this. All right, so every month, what is this population doing? All right, take a couple seconds, pause the video, take a few seconds, answer that question. From one month to the next, what is this population doing every single month? And come back and resume. All right, this population is doubling every month. All right, so from 0 to 1, it doubles to 2. From 1 to 2, month 1 to 2, it doubles to 4. From month 2 to 3, it doubles to 8, and so on. Okay, so what this tells us is that we can actually figure out a formula for the R's, the R sub 1, 2, 3, 4, 5, 6's, based on the previous R value. All right, let me tell you exactly what I mean by that. All right, so what this means is that, say, for instance, R6 is equal to 2 times R5. Right? Take R5, which was 32, multiply that by 2, and you get 64. And that is R6. All right, so taking the previous month and doubling its value gives you the next month. All right, that's true for any of them. R3 is 2 times R2. Right, if you check the numbers in the table, that is true. All right, and so this is the general idea. So let me just grab one of these values, kind of at random here. R5, right? I'm just grabbing one of them. I'm not starting at 5 for any logical reason. All right, so R5, I know is going to be 2 times R4. And I know that's going to be, I know R4, right? R4 is 2 times R3, right? Using the same logic. Right, so I can replace R4 by 2 times R3. Now I know R3 is 2 times R2. All right, so I can say that I have 2 times 2 times 2R2, like that. And now I know that R2 is 2R1 using the same logic. Right? So now I can say this is 2 times 2 times 2 times 2R1 like that. And, I know what R1 is. I'm just trying to get back to a reasonable stopping point. And let's say I want to go all the way back just to be 100% sure about what I'm doing. I'm going to go all the way back to the beginning of the experiment, which is R0. All right, so this last one I'll do. Let's see here, I'm running out of colors. Okay, so this last one I'll do. We know that R1 is 2 times R0. All right, that's the last one that we can possibly do. So this is going to be 2 times 2 times 2 times 2 times 2 R0 like that. And now we know from one of the assumptions in our model that R0 is 1. Right, so this is just 1. So what we really have here is the following. We've got 2 times 2 times 2 times 2 times 2. So this is 2 times itself 5 times. This is 2 to the power of 5. All right, you can double check your math just to make sure you didn't make a mistake. 2 to the 5th is 32, and that's exactly what we have for R5. All right, so we didn't make a mistake here in our math. That's always important to double check. So what we get is that R sub 5 is equal to 2 to the 5. So if you had to put money on it, R sub n is going to be equal to what? All right, work this out for a couple other values like R sub 2 or R sub 3 and see what kind of formula this procedure gets you. And then fill in the box for this prediction and submit that for proof that you watched the video.